Uh, this is my first national level presentation, sir. So please bear with me if any mistakes happen. Okay, sir, I'm audible, sir.
Yeah,
Sir?
Ranjit, you are audible. Please go ahead.
Yeah, yes, sir. I'm starting my presentation, sir. Good evening, everyone. First of all, I want to thank everyone for giving me the opportunity to present in this forum. Today, I'm going to present about the arterial physiology and hemodynamics. My plan of presentation is explaining the basic concepts of hemodynamics and its clinical applications in arterial disease. Whatever the arterial disease, the primary physiology comes under between the obstruction of the lumen or the disruption of the vessel wall. So we will going to see the hemodynamic basis of these obstructions and the disruption of the vessel wall. Let me explain the basic principles of arterial hemodynamics. Before going to the proper arterial principles, I want to explain two terminologies. The first one is the fluid pressure. The next one is the fluid energy. Fluid pressure in a fluid system is defined as the force per unit per area. It consists of three components: the dynamic pressure, hydrostatic pressure, and the static filling pressure. And fluid energy consists of potential energy and the kinetic energy. The predominant component of the potential energy is the pressure. The predominant component of kinetic energy is the velocity. So with this basic terminologies, I'm going to the principle proper. First, I will going to explain about the Bernoulli's principle. Bernoulli's principle defined as when a fluid flows steadily from one point in a system to another point, its total energy content along any given streamline remains constant, provided the flow is there is no frictional loss. This is in accordance with the law of conservation of energy. That means the total energy in the system is remains constant, but one part of energy can change into the another one. If that if there is an increase in potential energy, there will be a proportional loss of kinetic energy may occur. That means if there is an increase in pressure, there will be a velocity will be reducing. But this situation is not observed in the human artery because the ideal flow conditions specified in this Bernoulli's relationships are not present in the human arterial systems. So some part of energy loss may occur in the form of heat. So we will see that what are the energy losses occurs in the blood flow systems. In a energy losses in the flowing system occurs in the as two parts, either as a viscous loss or the inertial loss. Viscous loss occurs due to the viscosity of the blood. Inertial loss occurs due to the change in the velocity or the direction of the flow. First, let me explain the viscous loss. First, I will explain the viscous loss. Viscosity is defined as the ratio of shear stress divided by the shear rate. Shear stress is defined as proportional to the energy loss owing to the friction between the adjacent fluid layers, and the shear rate is explained as the relative velocity of the adjacent fluid layer. So, the clinical applications of viscous loss is using of the rheological agents. We are commonly using the rheological agent like low molecular weight dextrans and pentaxyclines are more often used in the immediate post-op period to increase the flow through the reconstructed arterial segments by reducing the viscosity. By the way, we are reducing the viscous energy loss of this flowing blood. The next thing is the inertial loss and the Poisson's law. Poisson's law usually states that the pressure gradient along any tube is directly proportional to the mean flow velocity and the volume flow and the tube length and viscosity of the bed, and it's inversely proportional to either 2 to the power or 4 to the power of the radius. So according to the Poisson's law, radius has the profound influence on the energy losses. So with this length and radius, the relationship between the energy losses is while you're doubling the length of the stenosis, the results in the doubling of the associated energy loss. But we reducing the radius by half, it will increase the energy loss by the factor of 16. That means the separate short stenosis tend to be more significant than the single largest stenosis. Or otherwise, multiple subcritical stenosis may have the same effect as the single critical stenosis. So, by inertial energy losses, if there is any variation in the lumen diameter or at the point of curvature or the branching, there will be acceleration and deceleration of the pulsatile flow will occur. It will lead to the inertial energy losses. The proportion of inertial energy losses is proportion to the square of the blood velocity. So, what is the clinical application of this Poisson's law and the inertial energy losses? So, when we plot a diagram between the pressure drops and and the radius, we can get a diagram like this. In this, the pressure drops is negligible when the diameter is less than up to 0.3 centimeter. If it's reduced to less than 0.3 centimeter or up to 0.2, the pressure drop is significant. There will be a significant pressure drops will occur. So this may give an explanation while doing the bypass graft why you are preferring arterial graft of not less than 3 to 4 mm in diameter. By the way, we are reducing the inertial loss of the flowing blood. Next concept I will move into the vascular resistance. The hemodynamic resistance can be defined as ratio of the energy drop between 2 points along the artery to the mean blood flow, or the pressure difference between the 2 points divided by the mean blood flow, as like the normal Ohm's law of the electric circuit. The standard physical principle of the hemodynamic resistance is the peripheral resistance unit, that is PRU. One PRU is equal to 8 into 10 to the power of 4 dynes per centimeter. The total vascular resistance in arterial system in the blood systems, arteries and capillaries consist of 90% of the total resistance, and venous consists of only 10%. Among the arterial and capillaries, uh, major component is the arterioles and the capillaries. It consists of more than 60% of the total vascular resistance, and large and medium sized arteries are the low resistance system. That is, the total vascular resistance is only 15% of this resistance, total resistance. So commonly, the atherosclerosis most commonly occur in the low resistance systems. That's why it predominantly occur in the large and medium size arteries rather than arterioles and capillaries. Next, applications of resistance is effects of resistance in series and the parallel. As like a electrical circuit, in the hemodynamic circuit also, it has some hemodynamic effects. We'll see one by one. The first thing is when you adding a parallel graph like a parallel resistance, like in the scenario while doing a bypass, fempo bypass, in a case of fempo percussion, surgeon occasionally express the concern over the possibility of the continued patency of the stenotic artery might lead to a thrombosis of the parallel graft. To allay this fear, surgeon most of the surgeon either they will avoid end to side anastomosis, or most of the time they will ligate the stenotic artery. But the theoretical consideration strongly suggests that such concerns are not valid, provided that the arterial segment is sufficiently diseased to merit the bypass grafting. Next thing in the parallel resistance system is while harvesting the vein, sometimes the saphenous vein bifurcate into two separate and parallel channels that rejoin after variable distance to reconstruct a single lumen. When this situation occurs, surgeon must to decide whether they have to include both channels or keeping a single channel. Which one is better? The answer is the combined resistance of two parallel channels exceeds than the single undivided vein. So the single channel is better than the keeping both channels. The next thing is adding resistance in the sequential resistance. So if a patient having both fempo occlusions and tibial occlusions, we can offer direct femoral to distal bypass or a femoral to popliteal bypass to the sequence bypass. Which one will be the better? According to the theoretical hemodynamics theories, there will be advantages and disadvantages for the both. If you're doing a femoral to tibial bypass, theoretically there will be a flow rate will be lesser than the sequential bypass. So the femoral to tibial bypass, direct tibial bypass having more likely to fail due to the reduced flow. But on the same time, the advantage of the femoral to tibial graft is some component of the blood from the on the sequential bypass get to uh, ligase to the proximal thing. So there will be some still may occur. It is not occur in the direct bypass. Next concept, I will move into the blood flow patterns. Blood flow either occur in the laminar flow or a turbulent flow. Laminar flow is in a steady state conditions, the flow pattern is laminar. The laminar flow is defined as all motions in the parallel of the wall of the tube. The fluid arranged in the series of a concentric layer are the laminar. While plotting this diagram, the velocity profile will occur in the parabolic in shape. With the velocity, that means the velocity being highest in the center of the stream and becoming progressively lower towards the vessel wall. The layer of fluid or blood in contact with the wall is stationary. In contrast to the laminar flow, turbulence is on an irregular flow status in which the velocity varies rapidly with respect to the space and time. The random velocity changes results in the inertial energy loss and the dissipation of fluid energy as a heat. To measure this, we are using a unit known as the Reynolds number. The Reynolds number defined as the point at which the flow changes from laminar to turbulent is best defined in terms of dimensionless quantity known as the Reynolds number. Normally, turbulence flow having the Reynolds number of more than 2000 and the laminar flow having a Reynolds number of less than 2000. Usually in the peripheral arterial system, the Reynolds number is less than 2000, so the turbulence is unlikely to occur in the peripheral arterial system. But in ascending aorta, during the peak systolic ejection phase, some turbulence may occur. Next concept is normal pressure and the flowing of the arterial systems. As the arterial pressure pulse moves distally, the systolic pressure rises and the diastolic pressure falls, and the pulse pressures become wider. Normally, the ankle systolic pressure is 10% higher than the brachial pressure. So, the normal AVA is in the between the range of 1 to 1.3 and not exactly 1. It's due to the increased intraluminal pressure from the gravity in the upright posture to the increased wall thickening and the unchanged inner radius, leading to the increased arterial stiffness. Next thing is the boundary layer separation. In a fluid flowing through the tube, a portion of fluid adjacent to the tube wall is referred as the boundary layer. This layer is subject to both frictional interactions with the tube wall and the viscous forces generated by the more rapidly moving fluid toward the center of the tube. So when the tube geometry changes suddenly, such as the point of curvatures and branching or in the variation in the loom of diameter, small pressure gradients are created that causes the boundary layer to stop or the reverse in the reverse flow in the reverse direction. These changes results in the complex known as the area of boundary layer separations or a flow separation. So this concept, when there is a flow disturbance occurs in the form of flow separation occurs, it will contribute to the formation of atherosclerotic plaque. In internal carotid artery, the atherosclerotic plaque commonly occurs in the outer wall of the internal carotids due to this flow separation and the low shear stress. Next thing, while constructing the end to side anastomosis, there will be some form of energy loss occurs due to these flow separations. To reduce this energy loss, the transition from the graft to the host vessel should be as smooth as possible. So the end-to-end anastomosis is the ideal one according to the hemodynamic principle. But while constructing the end-to-side anastomosis, we can reduce the pressure loss by reduce the angulation between the recipient artery and the donor artery. If it's in the acute angle, it will minimize the loss, but it can never eliminate the flow disturbances. Next hemodynamic principle we are going to see is the bifurcation and branches blood flow. When the branches of the arterial system produces sudden changes in the flow pattern that are potential source of energy losses. So the flow patterns in the bifurcations are mainly determined by two factors, that is the area ratio and the branch angle. Area ratio is defined as a combined area of secondary branches divided by the area of primary artery. For efficient transmission of pulsatile energy across a bifurcation, the vascular impedance of the primary artery should be equal than that of the branches. Ideal area ratio is 1.15 for a larger artery, 1.35 for a smaller artery. But in a normal infrarenal aorta, the area ratio is 0.8. So approximately 22% of the incident pulsatile energy is reflected. That's why atherosclerosis and aneurysms are more common in the infrarenal aortic segments. Next clinical application of area ratio is the commercial graft, bifurcation grafts. The ideal area ratio should be more than 1, that is 1 to 1.1 to 1.5 for aortic grafts. But despite of this theoretical disadvantages, commercially available bifurcation graft we are now using, sir, are less than the area ratio was less than up to 0.5, 0.7 ratio ranges will come. But it have functioned extremely well in a variety of clinical applications. Next thing is the branch angle. The flow disturbance are minimized when the angle is narrow and is exaggerated when the limbs are widely spread. The average angle between the human iliac artery is 54 degree. However, with a diseased or a tortuous iliac artery, the angle can be approaches 180 degree. So for getting this advantage of branch angle, while constructing a aorta bifem or a aorta biiliac graft, we are keeping the primary limb as shortest as possible. Next concept I will move into the bruits and the postnotic dilatations. Stenosis are irregularities of the vessel lumen produced by the turbulent flow pattern that set up a vibration in the arterial wall. These vibrations generate a displacement of waves that radiate through the surrounding tissues and can be detected as a audible sounds that known as a bruit. Generally, soft mid-systolic bruit is associated with the relatively minor lesions that does not significantly reduce the flow or pressure. But a bruit with a loud diastolic component suggests that stenosis having severe enough to reduce the flow and produce the pressure drops. A bruit may be absent when an artery is nearly occluded or when the flow rate is extremely low. Next thing is the post-stenotic dilatations. The post-stenotic dilatations most likely occurs in the arterial wall vibrations, result in the structural fatigue of the elastin fibers. In a series of animal studies, post-stenotic dilatations didn't occur unless there is a bruit was present distal to the stenosis. Next concept is the critical stenosis. The degree of narrowing at which pressure and flow begin to be affected has been called as the critical stenosis. The appreciable changes in the pressure and flow do not occur until the cross-sectional area of the vessel has been reduced more than 75% or more than 50% reduction in the diameter. But the critical stenosis in a high flow system, high flow velocity system, that is in carotid, renal, and the splenic system, so sir, reduction in the pressure with is less narrowing than the low flow system like occur in the peripheral arterial systems. Next, I will move on to the palpable pulses. The motion of arterial wall is responsible for the palpable pulses. However, 7 mm femoral artery in a younger subject would expand only 0.2 mm under the influence of 50 millimeter mercury of pulse pressure. And the stiffer arteries in the older individual would expand even less. The clinical value of the pulse palpation is based on assumption that the strength of the pulse is directly related to the pulse pressure, which should be decreased distal to the obstructions. However, stiff and calcified vessels may display a little or no palpable pulse, even though there is no decrease in the pulse pressure. Next concept, I move on to the arterial obstructions and the collateral circulations. In a normal hemodynamic circuit consists of a diseased main artery and and a parallel collateral systems along with a vascular bed, peripheral runoff bed. In this circuit, we have a two component of resistance, one fixed component and one variable component. The collateral system having a fixed component of resistance and the peripheral runoff bed having a variable component of resistance. Normally, in the resting state, the peripheral runoff bed having a higher resistance than the collateral systems. This peripheral runoff system consists of a runoff system resistance consists of terminal arterioles and the precapillary sphincter. Because of the small diameter and heavily muscled muscle wall, these vessels are ideally suited for the regulatory functions. This resistance is subjective controlled by autonomic nervous system, circulating catecholamines, and local metabolic products and the myogenic influences. This peripheral resistance system having auto regulations, while there is a pressure drops will occur, it will start to dilate. At over some point of time, in the vasodilation get exhausted. So this auto regulation can compensate for the pressure drop in perfusion only until the falls below the critical level. That is the skeletal muscle pressure less than 20 up to 20 to 30. It will start auto. With the pressure drops below this level, normal blood flow is no longer maintained, and the flow responds passively to the changes in the perfusion pressure. So the clinical applications of this concept is first one is for exercise therapy, mainly suited for the mild and stable claudication patient, not for the severe grade patients, because the peripheral runoff bed resistance system is already exhausted uh, due to the autoregulatory exhaustion. The next thing is the vasodilator. Vasodilator also it will improve the uh, peripheral vascular resistance only in the normal patients, but in the ischemic patients it won't work because due to the exhaustion of peripheral vascular resistance. Next thing is the sympathectomy. The purpose of doing sympathectomy is to reduce the peripheral resistance by releasing the vasomotor tone. It has no effect on the collateral resistance. It clinically improve only in the patients having an intact vascular resistance systems, which was documented by the reactive hyperemia test. Next concept I will move into the vascular steal. Vascular steal may arise when two runoff beds with different resistance must be supplied by a limited source of arterial inflow. It will be when external anatomic bypass is performed, a single donor artery must supply several vascular beds. In case of we are considering a femoral to femoral crossover, one iliac artery is the donor artery, and the leg ipsilateral to the donor limb is the donor limb, and the contralateral leg is the recipient limb. So studies of the crossover grafts in animal models have shown that immediate effect of the graft is to double the flow in the donor artery. When an AV fistula is created in a recipient limb, the graft flow may increase by the factor of 10 without any evidence of steal from the donor limb. The most important factor contributing to the vascular steal with the femoral graft is the stenosis of the donor iliac artery. The occlusive disease of the donor limb distal to the origin of the graft does not result in any steal. So the main important factor is stenosis of the proximal donor iliac artery rather than the distal thing. Next, I move to the effect of gravity in hemodynamics. Most of the patients with severe lower extremity ischemia discover that hanging their feet over the edge of the bed or walking a few steps often provides some relief in the ischemic restraint. The improvement in the peripheral perfusions also documented by the transcutaneous oxygen tension. The reason behind the increasing of the arterial perfusion is the increased hydrostatic pressure due to the dilation of the capillaries and microvasculars, thereby reducing that resistance and hence augmenting the blood flow. But this won't occur in the normal non-ischemic limb because of the intact veno-arterial reflex. So based on this all concepts and the Poisson's law, we'll tend to know that the radius is the most important in determining the both viscous and energy losses. So the graft selection should be primarily based on the radius of the graft. It should be large enough to accommodate any increased flow likely to be required during the exercise without any appreciable drop in the pressure. So this chart explains various diameter of the graft and the flow status. So it's clearly explained that graft size of less than 3 mm won't compensate for the resting and as well as the exercise. Which was I previously explained that therefore under most of the physiological conditions, the aorta of femoral graft with the 7 mm limb should suffice with the flow restriction only during the sternus exercise. However, 6 mm graft might begin to show some restriction of flow even with a mild to moderate exercise. The next thing is the pseudointima. The prosthetic grafts developed a thin layer of pseudointima over the period of time. Therefore, after implementation, 6 mm prosthetic graft might have an internal diameter of only 4 to 5 mm, and the 7 mm graft may have a luminal diameter of only 5 to 6 mm. So, for this reason, we only when performing any graft, it should be appropriate to select a graft with the original diameter of at least 6 mm. Similarly, the original diameter of for aorta femoral graft should be at least 7 mm. The meantime, it won't be too much larger than the recipient artery because the large graft will cause the thrombus accumulation in the inner wall of the graft with the due to the excessive diameter. So the inference from this is the diameter of the prosthetic graft should be small enough to ensure the rapid velocity of the flow, but large enough to avoid the restriction of the arterial inflow. Next, I will move to the shear rate. The long-term patency of the autogenous vein graft is compromised by intimal hyperplasia, the development of which has been associated with low shear stress. The low shear rate causes the smooth muscle cell to become secretory and enhance the platelet aggregation and increase the intimal hyperplasia formation. And higher shear rates foster the continued patency and lessen the tendency of the intima to become hyperplastic. Finally, I am going to explain about the hemodynamic basis of aneurysm rupture. The aneurysm rupture is mainly maybe explained by the tangential stress and the tensile strength. The rupture occurs when the tangential stress within the arterial wall becomes greater than the tensile strength. The tangential stress was measured by the Laplace law. The Laplace law defines as the tangential stress is directly proportional to the pressure on the inner radius of the vessel wall and inversely proportional to the thickness of the tube wall. So when there is an increase in radius and increase in pressure occur, the tangential stress will increase and it's more prone to rupture. That's why we are while doing the surveillance of the aneurysm patients, we are more bothering about the radius of the aorta, and we'll treating him with the antihypertensive modalities for reducing the pressure. Regarding the uh, tensile strength, the aneurysm rupture most commonly occur in the posterolateral aspect of the aorta. Due to the wear and tear changes more commonly occur in the posterolateral aspect, the tensile strength will be reduced. That's why the aneurysm ruptures most commonly occurs in the posterolateral part of the aorta. That's my presentation, sir. Once again, I want to thank everyone for your kind attention to